Okay, in the last lectures we have discussed about the structural or gate level modeling, and then switch level or transistor level modeling, then data flow modeling, and the last level of design description is behavioral modeling. So, today we will discuss about the behavioral modeling. So, normally if the digital circuit consisting of fewer gates, so a convenient way to model is by using structural or gate level modeling. Okay. Whereas, if the number of gates are more, then we have to go for the behavioral modeling. Okay. So, this behavioral modeling basically describes the digital design at algorithmic level. Or you can also call as abstract level or functional level. Okay. This is the high level modeling. Okay. So, basically this behavioral modeling will describe the digital circuit in terms of the function. Okay. So, that is if you want to explain in a clear manner. Okay. So, it describes what to do the designed circuit. Not how it is built on hardware. So, we do not bother about the internal hardware of the circuit, just we will consider as a block box. Okay. So, this is block box, we will give some inputs, then we will have some outputs. Then in behavioral modeling we will discuss what the function that will be performed by this block box without knowing the hardware inside this block. Okay. So, because of that this enables design of massive chips. Consisting of millions of gates. So, that is why in today's industry, so mostly we will use behavioral modeling, because the industrial application specific integrated circuits, they contains millions of the gates. So, in order to describe this behavior of this ASIC designs, so a convenient way is use of behavioral modeling. Behavioral modeling actually enables the looping, it enables the looping, it also enables the assignments, the conditional branching, so because of these features this resembles like C language program. So, we discussed about the various keywords used in the behavioral modeling while discussing about the introduction of Verilog lecture. So, this behavioral modeling basically I will call as BM, behavioral modeling. So, this basically uses the keywords always. This is similar to the data flow modeling, initial, begin and end. So, always as the name implies, so this will be executed in a loop. This will be executed in a loop subjected to some conditions. Whereas this initial, as the name implies, it executes only once. So, it will be normally used for setting the initial condition. Like if we take the ripple carry adder, what is the initial carry? If you want to set initial carry as 0, so we can initiate that C0 is equal to 0 using this initial block. And there are two more blocks, begin and end. Normally whatever the sequential statements will be written between this begin and end. Between these two keywords or blocks. So, to start with the examples, first we will discuss the combinational circuit modeling using behavioral modeling of combinational circuits. So, in that first I will discuss using Boolean expressions, okay, combinational circuit described in terms of Boolean expressions. If I take example of AOI gate, this stands for AND gate, this stands for OR, this stands for inverter. Let the gate is, say for example, we have two AND gates, one OR gate followed by one NOT gate. Say output is Y, inputs are A, B, C, D. So, the Boolean expression for this one is Y is equal to AB plus CD whole bar. Okay. Then how to model this using behavioral description. So, there are 4 inputs and 1 output. Okay. So, I will call this module, I will give some name AOI, output is Y, inputs are A, B, C, D. Output is Y, inputs are A, B, C, D. Then we need assign statement, assign y is equal to, so y is actually AB plus CD whole bar. A we have to AND with B, A AND with B. Here you can use a single AND operator, or you can use two operators if they are single bit numbers. If they are multiple bit numbers, then it will be different. Okay. So, here you can use a single AND operator, or you can use two AND operators, because A, B, C, D are single bit numbers. So, this is one bit number. So, all are one bit numbers. So, we can use either double AND or single AND, it is same. Similarly, double or single OR, it is same if the variables are single bit. C and D, this is not. So, the entire Boolean expression is represented by this statement, then end module. This is a simple Verilog code corresponding to the Boolean expression. Okay. Suppose if I want to check some condition. Okay. So, in the previous circuit, if I take a second example where I am going to add a buffer to this. So, if I use the same circuit, I am going to add a buffer with control signal. So, the output will be this expression y is equal to this if control is equal to 1. Otherwise, because this is inverter, this is what you have to implement for this circuit. Okay. So, the control signal is going to decide whether the output is the original expression AB plus CD bar, or output is Z. Z is nothing but high impedance state. So, we know that this buffer will be having 3 states: logic 0, logic 1 and high impedance state. Okay. In high impedance state, this will act as open circuit. So, this will not draw any current. So, if I want to write the Verilog code correspond to this, so these 3 statements are same, we call this as some A. So, A here, all the 3 statements are same. Then we can use a conditional statement. So, we know that assign output y is equal to C and TL, y is equal to C and TL question mark. So, we know that this is the conditional operator which you have discussed in earlier classes. So, what are the 2 conditions you have to check? The output can be if the control is logic 1, the first expression is executed. If control is logic 0, second expression will be executed. These 2 has to be separated by colon. Okay. The same this colon 1B Z. So, we know that the statement of this 1B is 1 stands for 1 bit, B is binary and the value is Z. Okay. So, if this control signal is true, the first expression is executed, this one is executed. If it is false, then the second condition, this is executed. then end module. So, this assignment is actually called as continuous assignment. When does this RHS right hand side will be assigned to the LHS left hand side, which is y, if any one of these variable changes. Continuous statement, this particular expression is executed, expression is evaluated, if any of the variables in RHS changes. So, whenever any variable changes, this will execute this expression and then it will be assigned to y. Okay, that is why the name continuous assignment. We can also write this program using wires. So, instead of writing single expression here, I can define here wires W1, W2, W3, W4. You can write using wires also. Okay. If you want to write using wires the same program, module, then call as here and or inverter and buffer also. Output is y, inputs are a, b, c, d. Output is y and one more input is there, enable, which is control, a, b, c, d, c and t, l. Output is y, inputs are a, b, c, d, control, and there are 4 wires W1, W2, W3, W4. So, first I am going to assign W1. So, what is W1? This is A, B, this we have called as W1. So, W1 is equal to A and with B. Similarly, W2 is C and with D. Then W3 is W1 or with W2. Then W4 is not of W3. Then the final output depends upon control. So, you can write the same conditional statement, assign y is equal to C and T L so it can be either Z or W4. Okay. W4 if it is true, otherwise 1 B Z, then end module. So, this is the Verilog code of this AND or invert buffer gate using wires. Now, we will discuss the other combinational circuits. First, I will discuss the multiplexer, 2x1 multiplexer. So, we know that for 2 by 1 multiplexer, 2 inputs I0, I1, one selection signal S, one output Y. If S is 0, output should be I0. If S is 1, output Y is I1. Okay. This is if else structure. So, this if else structure will be executed by always block module. This of course, we have already discussed in the earlier classes, I think. 2 by 1 mux, output is Y, inputs are I0, I1, selection, output Y, input I0, I1 is assign, output Y is equal to S condition. I think in the previous, the condition should be after this. S condition I0 colon I1 end module. So, we know that in gate level modeling, so in order to model the higher order multiplexers, we realized this higher order multiplexers in terms of the lower order multiplexers, and then we have instantiated. Okay. So, the similar type of the concept can be used for the behavioral modeling also. Suppose if you want to implement 4 by 1 multiplexer, here you have to use 4 conditions. So, like this, here we have 2 selection signals S1, S0, 4 inputs, and 1 output Y. So, S1, S0 is going to decide the output Y, 0, 0, I0, 0, 1, I1, 1, 0, I2, 1, 1, I3. So, if you want, you have to write this assign 4 such statements. Instead of that, using single assign statement only, we can write this. Okay. So, for that we have to realize this 4 by 1 multiplexer in terms of 2 by 1 multiplexers. So, as we have discussed in the earlier lectures, so this 4 by 1 multiplexer can be implemented in terms of 3 2 by 1 multiplexers in this manner. This is I0, I1, this is connect to 0, 1, there is another 2 by 1 multiplexer, this is I2, I3, internally this is 0th and 1st. Then the selection time signals of these two will be same as S0. Then these two will be applied to another 2 by 1 multiplexer. This is 0, 1, this will be S1. This is final output Y. You can easily verify this truth table will be obtained for this circuit. Okay. Now, we can use only single assign statement to implement this 4 by 1 multiplexer using this. Okay. So, what will be the code correspond to this one? Module 4 by 1 mux Y I0, I1, I2, I3, S1, S0, output y, input I0, I1, I2, I3, S1, S0. Then single assign statement, assign y is equal to S1, we are going to first find out this S1 condition. If S1 is equal to 1, so this has to be selected, 0 this has to be selected, 1 this has to be selected. Okay. So, this one has to be selected, I2, I3, I0, I1 has to be selected. So, this is 1 means this has to be selected, S0, this is also S0. One means I3, 0 means I2 is 2. So, this is correspond to, if I name this multiplexers as 1, 2, 3. So, this is correspond to 1 and 2 is in a similar way, we have S0 only, because the selection lines of these two are same, but the inputs are, for 1 it is I1, for 0 it is I0. So, this is for 2, this is for 1, and this entire thing is for 3. So, this parenthesis started here, it will end here, then semicolon, this is for 3. So, using single assign statement, so this is nothing but instantiating this 2 by 1 multiplexer, and then this is instantiating this 2 by 1 multiplexer, okay, to get overall the multiplexer, the end module. So, this is how you can use for the larger multiplexers, we can instantiate smaller multiplexer in a similar way to that of the structural or gate level modeling. Okay. Next, we will discuss about 2 channel 32-bit multiplexer. That is, we have 2 channels, each channel consisting of 32-bit numbers. This is data 0, this is data 1, this is 32-bit number, this is also 32-bit number, and we have only one select signal. This is 2 channel mux. Output is again a 32-bit number, you can call this as a out. So, either of these 32-bit numbers will be transferred to the output selected by this selection signal. This is I0, say this is I1. Okay. So, now here in the previous multiplexer we have a scalar, now we have vector. Okay. So, we can define the vectors, we know how to define the vectors also, that we have discussed in the earlier lectures. So, the code correspond to this one is module 2 channel mux out data 0, data 1, then select out 31 is to 0, output 0 out. This out is the signal name. Okay. This is 32-bit. Input 31 is to 0, data 0 comma data 1. Then another input is select, then assign out is equal to select data 1, because for true 1 has to be selected, is to data 0 in end module. So, if it is gate level, it will be much more complicated, because so we have 32 bit numbers, two 32 bit numbers we have to multiplex. So, it will take lot of circuitry, it will require complex circuitry. So, you have to explain in terms of the logic gates in case of structural level modeling. So, it will become complicated. See? Whereas, if I use the behavioral modeling, so we can write using only a simple Verilog code. Okay. So, next we will have some other combinational circuits such as decoders, and then we will discuss a small ALU also, sequential circuits. Okay. So, all those things we will discuss in the next lecture. Thank you.